Okay, hey folks, we're getting into our very last module of the semester. I know I'm excited about it. I'm sure you're excited about it too. For this last module, we're going to continue our discussion of molecular spectroscopy. This time, we're going to focus on the electronic transitions. So there's going to be a number of techniques involving electronic transitions that we will discuss. So in this first one, this will be largely a review of the photoelectric effect, so we can see how that relates to the first type of electronic spectroscopy we'll discuss, which is photoelectron spectroscopy. So if you recall, we discussed this topic at the very beginning of the semester, the photoelectric effect, Einstein's 1921 Nobel Prize. And recall, in the photoelectric effect, this describes the photoionization of a material, generally a solid under high vacuum. So let's note that. This is always on solid states under what I will call UHV, ultra high vacuum. And this technique typically has to be done under ultra high vacuum because we're liberating an electron from the surface of the material, and it's the electron that we are trying to measure. So under atmospheric pressure, that electron will get captured by a gas molecule very quickly. So as you imagine, we have to use a certain threshold wavelength of light to induce photoionization. So the way this all works is we start backwards with the kinetic energy of the electron as it comes off of the surface. And that kinetic energy must be equal to h nu, which is our incident photon energy. And that was written as h nu. We recognize now we could also write that as hc over lambda if we wanted to think about the wavelength instead of the frequency. And then now that's less the work function, which is the energy required to remove an electron. So for example, in this picture shown here, potassium, it requires 419 kilojoules per mole, or 419 kilojoules to remove 1 mole of electrons from 1 mole of potassium. So if we were to convert that 419 kilojoules into joules per single molecule, we could then convert that into either a wavelength or a frequency, so we could see what threshold value we need. And we would discover that a 700 nanometer photon is not energetic enough to do it, so we will not get any photoionization. But a 200 nanometer photon is energetic enough to do that, so we will get an ejected electron. So if we look at that schematically, recall we can make a line out of the photoelectric effect with the following. So if we recognize that here the kinetic energy of the photoelectron is on the y-axis, then we have the frequency on the x-axis, then our slope will be Planck's constant. Okay, slope equals h, and our binding energy will be the y-intercept. And so if you recall, if I trace these all the way down to their y-intercepts, we can see this lovely periodic trend is preserved where ionization increases as we go up and to the right. Sodium is higher up on the table than potassium, than rubidium, and you can see as we go up, that trend is preserved. So schematically, we can view the photoelectric effect as the following. So in this case here, my h nu is less than phi. No photoionization in this case where h nu is less than phi. Over here, however, where our h nu is greater than phi, we would get that photoionization. So this difference right here corresponds to our kinetic energy. Now, the way that photoelectron spectroscopy is done is, as I said earlier, we measure the kinetic energy of the electron. So you can imagine here we have our lamp. or could be an X-ray source, or could be a laser, or could be a synchrotron, depending on what wavelengths we're using. So this will photoionize electrons, and those electrons are what's being detected in this electrostatic analyzer, which works much like a mass spectrometer. Based on the trajectory and path an electron takes through here, we can determine what its kinetic energy was. So thus, by measuring the kinetic energy, so we measure this, we know the amount of light we are using, that is known. And so thus we can determine the work function, or in the case of photoelectron spectroscopy, that's known as the binding energy. Okay, more details on XPS and photoelectron spectroscopy in the next video.